Welcome to week 3 of electrical training. I hope everyone's doing well, staying safe. Yeah, let's get into it. So last week, we did an introduction to PCBs or printed circuit boards. We also introduced Eagle CAD, which is used to design PCBs. And we also started talking about the specifics of Eagle, mainly parts and libraries. We had you guys set up Eagle. I know there was some issue with that, so hopefully everyone got that resolved. If not, we can see what we can do during the lab part of this. And in last week's lab, you guys made a part. So uh, this week, we are going to first talk about communication systems, and then we are going to jump into designing schematics in Eagle, which is basically combining parts into what would eventually be put on a PCB. Also, reminder for dues, those are due on Saturday, October 10th. You can go to my.robojackets.org/dues to pay those. There's also some announcements in the Slack channel that has more details on that. So, all right. So we're going to start with communication systems today. So two basic types of communication, serial and parallel. So essentially, serial is when one bit is sent at a time, and it uses a clock in order to synchronize those bits. So as some examples of this are USB and SPI. And as you can see here, there is the device that's sending a signal to the other device. And you have a clock signal. And basically, these represent bits. So bit 7 is over here. And so basically, whenever this device, the receiving device, detects that a clock signal is on like the rising edge, there's also some falling edge ones, but standard is the rising edge. It will sample whatever is on the data line from out to in, and it will detect that as a bit and store it somewhere in here, and it can use that bit however that device specifically uses that bit. On the other side, there's a parallel. So this is when many bits of data are sent at the same time through different wires. With this, obviously, it's a little less efficient than serial because you do have to physically connect however many the amount of wires with however many bits you want to send at a time. This one also uses a clock in the same way that serial uses a clock, except you're basically sending more bits with each clock cycle. And some examples of this are PCI and DIMM, which is basically RAM. It is used on computer motherboards. All right, so I talked a little bit about this in the last slide, but clock signals are essentially square waves, so it'll go high, low, and this is basically and it has a frequency that is known to the sender and the receiver, which is also known as the baud rate. So as I said before, the edge of the signal is used to synchronize data. So essentially here it's using a rising edge as represented by the arrow. So you have your input signal up here, your clock signal here. So at the rising edge, it'll basically sample whatever's the signal at the input data line is, and then the device will read that at that certain clock at that certain point in time. And basically it samples at every dotted line here in this example. And that's how it'll synchronize the data between the sender and receiver. basically an example of like a clock signal is like your your processor might have like say 4 GHz. That's basically the frequency at which the clock is sampling at. So the higher the frequency, the more data you can send at a time, and therefore the faster your communication. All right, so we're going to get into some specific methods of communication here. So first one is SPI, which stands for Serial Peripheral Interface. This is obviously a serial system, and this specific system allows for bidirectional transfer, which is basically means that uh, in this case, the master and the slave can communicate with each other at the same time. So in this system, it is serial. So going in each direction is one wire, and and then obviously we have our clock, and in this case, the master controls the clock. So there's basically a wire going from SCLK, which is the clock pin. Those are connected between the master and the slave devices, and that's so that they sample at the exact same time. And then we have our MOSI, MOSI line, which is basically master out, slave in. Means that this is the line where when you want to send data from the master to the slave, this is the line that you would use. And then there's also the master in, slave out, which is doing the opposite. And then at the bottom, we have SS/CS, which is slave select or chip select. And that basically is used to decide is the master sending or receiving data from the slave. An example, so in this in SPI, you can also have the master connected to multiple slave devices. So if you had more slave devices, you would have to have another SS/CS signal for each of those devices, so it knows when it's communicating. Yeah, it's SPI. So we'll go on to I2C now, which is inter-integrated circuit. This is another serial communication method, synchronous, and this one is efficient, and this will be a recurring theme, but like the amount of wires that you have between devices, you want to try to minimize that. Although, of course, there are some trade-offs in that, but that is a goal of many of these communication protocols. So, similar to SPI, we have our SCL, which is our clock signal, and that is connecting the master and the slave so that they operate at the same clock signal. And then SDA is our data signal. Now you'll notice that there's only one data signal here. So essentially what I2C allows you to do is it minimizes the amount of wires by allowing bidirectional transfer over one line. And this is done through sending data in frames. So down here you would have your message. So essentially what you have is you have a certain start condition, which will be whatever the specified start condition is, a certain series of bits. Then you will have your address frame, read-write bit, which determines whether the master is writing to the slave or the master is reading the data from the slave. Then you have your data bits down here, and then you also have our stop condition. So that's how I2C works for two devices. Another benefit of using I2C is that any device can claim master by controlling the clock. So there's also certain built-in clock features where if the slave, I believe if the slave blocks the clock signal, It'll stop transferring, but then it can also control the clock signal for it to transfer. All right, the next communication protocol is UART, Universal Asynchronous Receiver Transmitter. This is different from the synchronous methods that we were just looking at, which use a clock signal. This one is asynchronous. Um, Basically, the benefit of UART is that you can input a parallel device data bus into the UART, and then you can use the UART to then transfer that to a serial device, as you can see with UART 1 and 2 here, and then that can then transfer back to a parallel. So again, with the recurring theme of being more efficient with wires, if moving signals across long distances in like a chip or in your PCB, this would be useful. So one thing to note for this is that both of the UART chips would need to have the same baud rate or frequency rate. This is so that you can imagine if they're clocking at different frequencies, then everything's going to get all messed up. So that's something that chips using UART would have to take into account. So here we have our TX and RX pins. So TX basically means transfer, RX means receiving. So you would transfer out through the TX to the RX pin of the other one, and vice versa if you are receiving. All right, so now this is USB, so Universal Serial Bus. Essentially what this is a differential pair signal. So it basically has a voltage signal that is used to then decode into bits. And so basically this will then create a packet, which is similar to the message that we talked about with I squared C. And then that can be used when receiving data. So this is very common, obviously, as many of you know, with certain computer peripherals, so mouse, keyboard, anything like that. What happens is that the USB signal will then go into a hub, an internal hub in the computer, and then that will then communicate with the main processor. Yeah, so then so this is essentially, I'm pretty sure this was talked about a little bit last week, but 18 mega 32U4 is a microcontroller. It's a standard one. A lot of the teams use it right now, but this is just for an example. It is useful to use data sheets. You'll be looking through data sheets a lot in your RoboJackets and your time in RoboJackets. And data sheets are very useful for every device. For microcontroller specifically, determining what pin does what. Because you get a small microcontroller, it's like a millimeter by a millimeter or something like that, and they don't label everything on it. So basically, you use the data sheet in order to determine what pin does what and what pin has which capabilities. So this is taken from the datasheet for the 18 mega 32U4. And as you can see here, we have our pins 1 through 44, and each one has a different label next to it. So if we look at pin 23, that's our ground for the chip. We also have multiple other grounds here. VCC on 14. And then other pins do specific functions. So we have pin, so we'll have see like pin PA whatever through whatever, PB, whatever through whatever. Each of these will have certain functions. So if we look at, say, pin B0, so PB0, we can see that that has SS, which is slave select, and then PC into, which I'm not sure exactly what that function is, but um, basically these show off what each pin is capable of doing. So some of them are ADC, so analog digital converters. Some of them can't take in analog signals. Um, but yeah, so using a datasheet is essential to working with these devices and can provide a lot of useful information if you're stuck on something. All right, so now we're going to get into Eagle and creating schematics in Eagle. So last week we installed Eagle. There was some issue with that, or if you couldn't make it last week, it is free for students, and you can get that installation started now if you don't have it, but I imagine pretty much everyone has it. So um, I know there are some issues, so we'll try to help you out now if you guys haven't been able to figure that out. Not now, sorry, during the lab section. All right, cool. So when you first open Eagle, this is the first window that's going to come up. This is the control panel of Eagle. It'll have some like news and stuff, tips and tricks, but mainly what we're concerned with is on the left side. So this is where you can import libraries, you can save certain designs that you have. Uh, Essentially, since RoboJacket's teams use GitHub, most of your files will be saved within the GitHub folders. Um, so you will most likely access it using GitHub, so you don't really have to worry about saving design blocks on or opening design blocks on Eagle itself. But this is essentially what you'll first see when you open up Eagle. You guys worked with it last week, so I'm not going to go too much more into it. So for today, our goals is to give you guys a good idea of how to create schematics in Eagle. So on the right side here, we have an example of the ATmega32U4, which I was just talking about with the pin configurations. And this is a, a snippet of a circuit that uses the ATmega in it. We are going to talk about how you would go about doing all this schematic wiring. So yeah, like I said, we're going to teach you how to make something like you saw on the previous slide. And yeah, if what you just saw seemed intimidating, don't worry about it. All of the trainers here were in the same position as you whenever we went through training. Hopefully by the end of today, that'll seem a little less scary. All right, some useful features to know. So we have our sidebar. This is in the schematic file when you would create one. So we have our sidebar on the left. This has actions and tools that Eagle allows you to use. So you have a move function. You can add parts. There's an add parts button over here. ERC, which is electrical. Electrical. Okay, I kind of forget what it stands for, but we'll get into that later. But essentially, any function that you need to any function that you could possibly need to do will be on the left side here, and just quick access for you. So then we have our command line. You can also get to the functions using this as well as some other ones. There's a useful command that if you don't have a mouse, you might want to do. Essentially, in order to pan around the schematic, there's no way to do that on a touchpad. On a mouse, you would like click down on the scroll wheel. But there's a command to like bind that function to a key on your keyboard. So that might be useful. Just an example of how the command line could be useful. All right, so searching for parts. This is the window that will come up when you hit add parts and you're trying to add parts to your schematic. In the area where it says name description right above the search bar, if you have nothing there, it'll show all of the libraries that you have available to you, which store obviously all the parts. So here it's showing a specific search function, which is called a wildcard, which is essentially a general search. So it won't look for things that are 100% specifically what you put in the search bar. It'll search for items or parts that have that phrase somewhere in its description or name. So here, searching for a R0603 resistor, which is 0603 is the package that it comes in, which is shown on the right side, that little 3D model in the top right. Without the wildcard, the only things that would come up were things that have that match specifically. So with the wildcard, it shows many more options for us. And this thing will make your life so much easier. Not using this, there's no reason really not to use it, because a lot of the parts have more specific names once you get outside of like resistors and capacitors and things like that. All right, so this basically summarizes what I just said. You place an asterisk before and after whatever you're searching, and it will do the wildcard feature. And please don't forget it. So here we have some Eagle resources which contain a lot of other useful walkthroughs of Eagle features. This is located in the RoboJackets GitHub. So you could go to that for that. I'm not sure if you guys get access to these slides, but you could also just click on these here. And then you could also go to our YouTube channel, which has useful resources there too. All right, so how to build your own schematic. First thing you want to do is grid lines. So if you look at the top here, there's a button that looks like grid lines, or you could type grid into the command line. Once you click on that, it'll open up a menu, and in that menu, you want to set a certain few things. So you want to make sure that the display is on. You want to make sure your style is line. Size is 0.1 inches, and alt is 0.01 inches. So essentially, how we came up with these things is that it's basically just a standard that here at RoboJackets we like to use. There's an Eagle style guide document that has even more standards that we like to use here. So you could reference that if you forget these numbers, but yeah, that's essentially what we like to use for when we design schematics. And since you have the display on, the schematic will now have grid lines on it. All right, next up, we want to specify our library. So you're going to want to go to Library and then Open Library Manager. And then it'll open up a window like this. As you can see, there's 3 tabs at the top. The only 2 we're really concerned with at this point are in use and available. In design basically just means which libraries have parts that are in your schematic, which isn't the most useful thing for now, but if you end up deleting libraries, it might actually be useful. So available libraries it'll essentially have all of the libraries that you have in that Eagle has in it, that's in Eagle's directories. So we can talk about that more later. I'm not sure if that was talked about already, how to add parts to the Eagle directory. Um, but that's where all of these will show up. So, for example, we added RoboJacket's Eagle libraries here into the path for libraries in Eagle, and they show up here under available. So the in use tab essentially has all the libraries that you can use for the specific schematic you're creating. So every time you make a schematic, it will have certain default libraries there, but it won't always have all of the libraries that you're interested in using. So in order to add libraries from the available library list into your schematic or into in use, you would highlight any of the libraries on here that you like to use and then simply press use. And then that will add these libraries, uh, make these libraries available to use in your schematic, and then you can add parts from those into your schematic. All right, and then here is just a side note on adding libraries that might not be in available yet. So you can browse for other libraries that you have on your computer and directly import it like that. It would probably be a good idea to, however, to add those libraries that you're intending on using into available, uh, so that you can just easily transfer it over like that. All right, so step 3, we're getting into actually creating the schematic now. So step 3 is adding parts. So depending on what you're doing, you can use the search feature as well as the library feature that we described in the last few steps in order to add parts to your schematic. So in order to do this, there's the button on the left sidebar, which will pull up the list of all available parts in each library. And then you can search for those parts. Search for the part that you need using that. All right, so once you have a part, search for, you can double click it or press OK once you're highlighted over it. And then that will be put onto your schematic. It will actually be like connected to your mouse, and then you have to left click in order to put it on your schematic. But essentially, it will be in your schematic. All right, then once you have your part down, you will most likely want to rearrange it in some way. So Eagle allows you to move the part and also change the orientation of parts. So there's a move button on the left bar, on the left sidebar. And if you select that and then click on a part, you'll be able to move that part. There's also, so the move button can also be used to rotate. You can right click while you're moving a part in order to rotate it. Or you could use the rotate button, which is located right under the move button on the left sidebar in order to rotate. So those buttons are shown here. You can use those to rearrange your parts however you like. All right, so next up, very important, is setting the value of your parts. This is obviously used to understand the schematic as a whole, and to know what parts you eventually want to buy to put on your PCB. So in order to set the value of parts, there's also a button for that. So you could click value on the left sidebar or type value in the command bar. And then left click on the part that you want to add a value to, and this window will pop up, and then you can add a value to that. So it's also good to note that you should have units in there somewhere. So the ohms, anything that like volts or whatever. But it's useful to have that. Just be diligent and be specific with the units of your parts, just so you don't forget or you don't get lost. All right, so next up is an extremely important feature. So this is adding and deleting nets. There are a few other features with nets that we'll talk about later on that are also important. But this is essentially what you use to connect to parts. So there's of course also a button for this on the left. It's the little green line towards the bottom. You can click on that, and this is used to connect parts. So you can click on the output, the pin of a certain part, and then you can drag it to another part, and then those parts will be connected. And then if you make a mistake, you can delete it or Control Z, however you want to do that. But yeah. Okay, this is also good to note. So when you hover over a parts pin, you should see a small circle show up, and that's when you can make the physical connection to that part. All right, so that is shown here. It's a little small, but you can see the crosshair or cursor is near the top of this diode, and that little green circle comes up. That means when you press down or when you left click, it will make a connection, and then you can connect that to wherever you'd like. All right, so now this is an optional step. Not really optional, to be honest. This is extremely used used a lot in your PCBs when you're designing them. So so name and label. So essentially what labeling allows you to do is to connect pins that might be on different sides of the schematic, super far away from each other, without having to physically route a net between those. So I'll just start with name for now. So name, pretty self-explanatory, allows you to give a part name. So if you have like, 10 resistors or something, you could go like R1, R2, R3, R4, all the way to R10, just to specify, the difference between certain parts. From there, you can use the label tool at the end of a net connected to that part, which that might have sounded confusing. I'll go to the next slide in a second. In order to connect a label. So another standard that we have here is making sure that the label setting is trapezoidal and that the size is set to 0.05. So I'll show that here. So here we have a net coming from this chip here, which is the green line, and it was set to the net was then the name tool was pressed on the left side, and then the net was selected. Then that window came up, and then you could label the net or put a name on the net. And then there's this little checkbox here, which says place label, which is something you want to do. When you press OK, it's actually not shown here, but for the label, when that comes up, you want to make sure that it's in this right trapezoid format. There's also this left one, which just has the name floating above the net, which isn't very useful or very nice to look at. And then you also want to set it to a size of 0.05. This says 50 because probably the units are off, but that's something that can be looked up in the Eagle style guide that we have. And so after you do that, this will appear at the end of the net, and this is a label. So yeah, so let me go back to this. So then from here, what you can do is say you have another chip on the far side of the schematic, you can do the exact same thing for a certain net over there. And those will be, as long as you give it the exact same name, those will be connected. Eagle, like they won't be connected physically, they'll be connected through the net or the label. But when you actually do routing, which we'll talk about next week, those will be physically connected. It's just a way to keep your schematic less cluttered and looking nice, since it's not the actual physical way that the PCB will look. All right, so next step is electrical rules check, ERC. And this is basically Eagle's way of telling you if something looks off, something just like maybe a net isn't connected or something like that. This is what that is used for. So this also has a button on the left side, ERC. And when you click on it, it will run a little program in the background, and then there will be a you will either get warnings or errors, or you won't. So if there's no warnings or errors, in the bottom left corner, there should be a short message about that. But if there is a warning or error, there will be a page that pops up, which will go into detail about what specific warnings or errors there were. So yeah, so here, this is the window that would pop up, and it'll show you, it'll have errors, warnings. And then from there, you can see what's wrong. Here, the unconnected pin D1, so D1 wasn't connected, which is, it's blocked here, but the bottom side wasn't connected to anything. So then in this window, you could either approve an error or warning, meaning that like Eagle caught onto something, but it was meant to be that way. Okay, that's fine. And then that error will go away. So if not, you can also just go back into the schematic and fix that error yourself. And then come back to the run the ERC again, and then that'll show you if that error was resolved. And this is just showing the no error message in the bottom left. This is what it'll look like when you run that, and there's no error. And also here you can see that the D1 diode was connected to this control. All right, so that was everything we had for this presentation. Now we are going to get into the lab. The lab is essentially having you guys work with creating a schematic. There's actually a template schematic that you guys will use and then add parts from that. But yeah, we're going to get into that now.